Now in this video, we will have a look on scattering phenomenon, and the motivation behind this video is basically to have a know how the classical scattering works, and how the quantum scattering works, and what's the possible difference between quantum scattering phenomenon and classical scattering phenomenon. And we can say that that we can have our approach. We'll not go into the details of the mathematical formulation, but we'll certainly write down the results of the formulations that are based on classical and quantum assumptions. This scattering is a very important mathematical formulation. Scattering theory is essential in understanding how particles interact, and it finds its application in maybe in nuclear physics, in particle physics, and also in condensed matter physics. Now, if I go with the basic setup of classical scattering, in classical scattering, what we do is we analyze the motion of the particle, and we analyze it under the influence of some central potential, V of r. So we have some potential V of r, and we analyze the motion of the particle that's interacting with this potential. And the motion of the particle in this case is purely governed by Newton's laws. So we have so the point is that we have trajectories here, and the projectile comes and it interacts with the potential. So the key parameter here is the Newton's laws, and there are some terms that are involved in classical scattering. The very first one is what we call as impact parameter. Impact parameter. And this impact, as all of you know, this impact parameter is symbolized as B. And what is this impact parameter is? It's basically that you have an impact, and what's the perpendicular distance from that impact from its initial trajectory of the particle. So I should say that this impact parameter is the perpendicular distance between the initial trajectory and of the particle and the center of the potential. So there is a perpendicular distance, and this perpendicular distance is my impact parameter B. And the next important thing is scattering angle. So scattering angle, and this angle is, say, theta, and it's basically the angle by which the particle is deflected from its original path. Suppose this was its original path and it has a deflection with respect to its original path. This angle theta is our scattering angle. And certainly this scattering angle will come in action only when the particle interacts with the potential. Now the question arises, what is a scattering process? How do we understand what's the basic concept of scattering process in the realm of classical physics, in the realm of Newtonian physics? So if I go with that, and what I have a particle. This particle is it approaches the target. So we have a target, and this particle moves towards the target and interacts with this target via the potential, and assuming that potential to be V of r, and is deflected. And to describe this deflection, what we do is we simply calculate or we compute the classical trajectory of the particle. And how do we calculate that? We calculate the classical trajectory using Newton's equation. Now, we can have Newton's equation. And what's that? That is mass into acceleration is force, and force is negative gradient of potential energy. So this is the basic equation that we compute, that we execute to learn about the dynamics of the motion of this particle that's interacting with this potential. And what this equation does, this yields the trajectory. It yields r of t, from which we can calculate what we have, that scattering angle theta. Now, there are a couple of more parameters, like differential cross section, that's used in classical scattering. Differential cross section. And this differential cross section, we define it mathematically by d sigma by d omega. And d sigma by d omega gives us the measure of the differential cross section. So how it measures? It measures things likely. It's for a particle to be scattered from the angle. So this d omega is giving us the measure of this angle. And which angle is this? This is the solid angle. We have d sigma by d omega, and d omega is our solid angle. So this is our d omega for the central potential that's under consideration. And it is related to impact parameter and the scattering angle. So we'll not go into the details of that. We'll write down the result. The result is B by sine theta, magnitude of dB by d theta. Why this d omega is our solid angle. And this B is a relationship between our, if I write down this, if we see the mod of this, there's a relation between the impact parameter and the angle. And angle is our scattering angle, theta here. Now, if we extend this argument to Rutherford's scattering, now for Rutherford's scattering, we have Coulomb potential. V of r is Z1, say Z2, and then E square by 4 pi epsilon naught r. This is our potential energy between the particle that's interacting with the potential of the nucleus, where Z1 and Z2, they are the atomic numbers. So classical scattering leads to this famous formula, d sigma by d omega. This d sigma, I'll not go into the details of it. We obtain this result as Z1, Z2 E square by 16 pi epsilon naught E times 1 by sine fourth of theta by 2. Now this is our classical scattering formula. This is the famous Rutherford's scattering formula. And d sigma by d omega is giving us differential cross section. And what does this formula do? This formula describes the scattering of the charged particles by the heavy nucleus, because obviously we have a charged particle and it is interacting with the potential of the nucleus, and showing that most of the scattering occurs at, we can check it analytically, for small values of theta we will have large differential cross section. We'll have large differential cross section. Now, from here, so the point is clear that that this formula is showing us that most of the scatterings occur at small angles. Now, switching to the quantum theory. Now, when we switch to quantum theory of scattering, in quantum theory of scattering, the incoming particle is treated as wave. It was a particle in case of classical scattering. Now you have an incoming particle, it's treated as a wave. And rather than that of the particle that we have used it in case of the classical scattering. And the interaction with the potential modifies this wave. So here we have modification. So suppose we have some kind of potential and this wave interacts with this potential. And what this potential does with this wave is it modifies the wave. And when it modifies it, we have a scattered wave. That could be the argument. And the main quantity of interest that we have here is what we call as scattering amplitude. This is of scattering amplitude. This is of utmost importance here. And this scattering amplitude can be symbolized as f of theta. It can be a function of energy. It can be represented by anything, say some momentum P1 and P2 and so on and so forth, and some K1 and K2. And it's this scattering amplitude which extracts the information, which extracts the probability amplitude of the scattering at a given angle theta, if I go with this, and at some specific energy E. Now here in this domain, in the classical domain, we have the Newtonian equation. But in quantum domain, the scattering process is described by what we call as time-dependent Schrodinger's wave equation. So time-independent Schrodinger's wave equation. And what's that? I can write down that minus h cross scale by 2m, then del scale psi of r plus v of r psi of r is E psi of r. Well, this psi of r is the wave function of the particle, and E is the energy. It's the energy of this particle. Now for scattering, so this is my basic equation. Now for scattering, the solution of the Schrodinger's equation far from the scattering region. That means if I write down its solution, if I have a potential V and I want to solve this Schrodinger's equation for the potential for the particle which is very, very far away from this potential, wherefrom it can have scattering, where if this is the scattering region, say for the sake of argument, then the particle is very away from this potential, and we have the solution for this Schrodinger's equation, and that solution is nearly like this. If I assume that there's a direction, e to the power of I k z plus f of theta and e to the power of I k of r divided by r. Now, the term that's this e to the power of I k z is the incoming plane wave. And the term, that's this term, this is the outgoing spherical wave. Now, the scattering amplitude that we have here is related to probability of scattering in the solid angle. So, if it has the relation with the probability of scattering into a solid angle, then I can say that this the differential cross section d sigma by d omega is nothing but the square of amplitude of f of theta and e. So this is our outgoing spherical wave, and if I take its complex conjugate, multiply it down with that, it's going to give me the differential cross section. Here it's this f of theta and e is a representative of scattering amplitude. But if I take the mod of square of this whole thing, this gives me the measure of the differential cross section. And what I see that differential cross section is it is proportional to the modulus square of the scattering amplitude. Now there is another approach that's used in quantum mechanics, and that's partial wave expansion. Partial wave expansion. The partial wave expansion is basically an approach, or we may call it a method, for solving the Schrodinger equation in presence of the central potential. Now see, in the previous case, our wave was very, very far away from the potential. So the interaction was very less. But here, this partial wave expansion is exploited in presence of the central potential. And doing so, the solution of the Schrodinger's equation, the scattering amplitude, is expanded in Legendre polynomials. Legendre polynomials, as all of you know, PL cos theta. So what we calculate is the amplitude of scattering f of theta and e is sigma 2L plus 1, and then FL of E and PL cos theta. Now this is our magnitude of scattering amplitude, where this FL of E that I have introduced here, they are basically the partial wave scattering amplitudes. Partial wave scattering amplitudes. And for each angular momentum, because we can have a range of angular momenta, for each angular momentum quantum number L, we have FL of E. And the partial wave amplitude, this FL of E, they are related to the phase shifters, because there is shift in the phase, because your incoming particle is a wave, it's interacting with the potential, and there is an equal probability of having phase shift. And this partial wave scattering amplitude, that's FL of E, it is equal to e to the power of 2I delta L minus 1 by 2ik. Now, the phase shift here is over delta L. What does it do basically? It describes how much the wave function is modified once there is an interaction with the wave function. It gives us the measure of that. This delta L is the phase shift. Delta L is phase shift. And it gives us the measure of how much there is modification in the wave function due to the scattering potential. And there are other approaches which we use here, like Born approximation. And these are the basic tools that are actually utilized to obtain the solutions to the problems of scattering. And Born approximation is another one. And in Born approximation, what we do is we assume that we are interacting, but we are interacting with a weak potential. And I'll make another video on Born approximation in detailed form, where we will have the Born formula and the last. But here I'll give you an idea. So what does this do? This Born approximation, it provides us a method to calculate the scattering amplitude. And to have the first order Born approximation, if I choose the same parameter as theta and E here, this nearly comes out to be 2m by h bar square integral e to the power of minus I q dot r v of r d3 of r. And in the forthcoming videos, when I'll extensively discuss Born approximation, here I'll not have theta and E, I'll be dealing with kk dash, and depending on the circumstances. And we will have an equation like this. And this Q, you will see, it will be there as k final minus k initial, where k is our wave vector, which has a relation with the momentum space. And this gives us the measure of transfer of momentum. Now, in simple words, I want to make a comparison between classical scattering and quantum scattering. Classical and quantum. I have bad handwriting, I can't do anything with that. What happens in classical scattering is that we treat particle as a point-like object. We have a point-like object. And this object follows the deterministic trajectory, where we can determine everything about it under the influence of the potential. And for quantum scattering, what it does not treat our particle as a particle, it treats our particle as a wave. And this wave is described by the wave function, a state vector, a wave function psi. And this wave function has a nature of spreading. That's it. And we have classical differential cross section. Now, in classical differential cross section, now in classical scattering, this differential cross section, what I defined as d sigma by d omega, is determined by the relation between the impact parameter that I talked about and the scattering angle theta. So we utilize those two parameters and we calculate d sigma by d omega. And in quantum domain, differential cross section is given by square of the scattering amplitude. So d sigma by d omega is my scattering amplitude. Then this scattering amplitude here is it's mod of f of theta and E whole square. And this thing, what it does basically, it includes interference. because we are treating our probing particle as a wave, so it has inculcation of interference effects. And these interference effects are not present in classical domain. They are not present in classical scattering. There's nothing like interference here. There's a complete exact interaction. And if we think now in terms of the angular dependence, in classical scattering, the scattering angle that we have theta here, it's determined by the specific form of the potential that you have. You can determine theta with respect to the symmetry of the potential and the impact parameter. But in quantum mechanics, the scattering amplitude, what is that? That is f of theta and E, has a more complex angular dependence, including those quantum interference effects and the contributions of the partial waves that are circulating this unknown dynamics that's going on there. And there is another important thing is that there are things in quantum scattering which are purely absent in classical scattering. And in quantum mechanics, what quantum mechanics does here, it introduces the phase shift, as I was talking about, delta L, which describes how the scattered wave is altered due to the potential that's surrounding that wave. And there's another important parameter in quantum mechanics, and that is the phase shift. When it passes through pi by 2, corresponding to some temporary kind of trapping of the particle in a quasi-bound state, we have resonance here. And resonances occur. They occur because of the phase shift. And resonance certainly has something to do with the maximum amplitude. So these things do happen here. And these resonances have no classical analog. We don't have any resonance here when a particle is interacting with the potential of the nucleus. Wavelength is another important parameter. There is another important parameter, that's wavelength. In the classical limit, where we have a de Broglie wavelength, lambda, of the particle becomes much smaller than the scattering region, quantum results simply tend to the classical results. So the point is that if this lambda is very small in comparison to the area of concern, in comparison to the scattering region will be a scattering region. If this is very, very small than that of the area of the scattering region, then we have the classical limit there. And quantum results, in those cases, they are approximated to classical results. So in this regime, the quantum phase shifts become large and interference effects become negligible, and they no longer have a role if the wavelength of the particle that's interacting with this scattering region. But in quantum regime, the interference effects play an important role. They play a critical role, leading to the patterns like diffraction. Diffraction in scattering. And these diffraction patterns have no classical analogs. Energy dependence. Classical scattering depends primarily on the initial energy and the impact parameter. The initial energy of the particle interacting with the potential and the impact parameter B. And there is no interference. But quantum scattering has a rich energy dependence with features like resonances. Here you will have resonances. You will have thresholds for scattering. And you will have scattering channels. You'll have scattering channels. linking those quantum tunneling kind of things. And you will have interference between different partial waves. And example of, if we take an example of Coulomb scattering, the differential cross section falls as in case of Rutherford, this d sigma by d omega, it falls like 1 by sine 4 theta by 2. In quantum scattering, the cross section exhibits the same angular dependence for Coulomb potential. Same, but quantum mechanics introduces the additional effects like interference, as I'm talking about, between the partial waves and the possibility of bound states like that of hydrogen atom. So for Coulomb interaction, the two phenomena have the same results. But in quantum regime, there is an additional thing, and that additional thing is because of the wave nature of the particle interacting with the scattering region. Now, to conclude this talk, I mean, both classical and quantum scatterings, they are very important. They are charismatic tools that are used in the framework of understanding the particle interactions. In classical case, scattering is described through deterministic trajectories, can exactly predict where the trajectory of the particle is, and impact parameters, while quantum scattering introduces the wave phenomenon, interference, and phase shifters. Now, quantum mechanics provides a more complex picture, and especially at small length scales and low energies, where wave effects dominate. But on the other hand, in high energy or large scale limit, quantum scattering results converge with classical predictions. That is the aim with classical predictions. So with this, I would like to end this talk. Okay, that's it. Bye.